Hello viewers, and welcome to a new STM32 World Tutorial video. Today we are going to go back to some of the earlier stuff that we did and talk a bit more about some of the advanced timer features in STM32. Now, I'm not going to lie to you, it is getting harder to come up with new ideas. I have made about 60 something videos by now, and it's getting harder and harder to come up with new ideas. But going through some of my stuff, I realized that back in video number 18, we were talking about using a timer to actually do count of a rotary encoder. Go back and watch this video. It is quite an interesting feature of the timer. However, the feature that it actually uses in the timer is the timer's ability to capture events and count those kind of events. That is called input capture in timer speak on the STM32, and there is actually a lot of other ways that input capture can be used, and in this video we are going to use the timer to measure frequencies. It's going to be quite interesting, so please stick with it, and we'll see where it takes us. Now, for the setup today, let me show you that. I have, oh, that didn't look, wait, wrong, there. I am going to use the black pill board, and I have hooked that up to my oscilloscope, my toy oscilloscope. It's not a serious oscilloscope, but it's good enough for what we are going to do here. So that's the setup for today. So as usual, let's get started with this. As usual, I have created a new project, and that will of course be in the STM32 Fun repository, and it's called Black Pill Timer IC for input capture. I have set it up standard with the crystal, the lead pin, the single wire debug up here, and a UART. I have also configured the clock to the correct crystal and running at 100 megahertz. Before I forget it, because we are going to need these numbers later. Over here, one of the reasons I use the black pill for this one is that both the timer clock buses are the same, and they are running at 100 megahertz, each of them, and that just makes the calculations a lot simpler, so I can do it in my head without actually having to look it up. So that is the basic setup. I have, based on that setup, created a standard source which have the redirect of the UART, and apart from that, all it does is print out a statement, and then it blinks the LED every 500 milliseconds, and it prints out a statement every second. So let's try to run this one. There, and where is it? Let's look at the output. The output is there, and as I showed before, the LED is indeed blinking. So that is the basic. Now let's generate some frequencies that we can later measure. So first step would be to set up a timer, and I am going to use a timer 4 as an output, and I give timer 4 a clock. I'm just hooking that up to the internal clock, and then I'll do PWM generation channel 4. The reason I'm using channel 4, if you watch there's no good reason for this one, but if we look here, I have actually some other stuff hooked up to this particular black pill board, and one of the ports that is using is the normal channel 1 port. Doesn't matter. I'll use channel I'll use timer channel 4 on timer 4. Channel 4 on timer 4. Now, I'm going to play with frequencies and duty cycles, and the easiest way to set this up would be to run with a counter period of 99, because if I'm using 99, I can set a percentage. So 10 will be a duty cycle of 10%. If I go up to 90, it will be a duty cycle of 90. If I set it to 50, it will be a duty cycle of 50. So it just makes it easy to calculate. What else do we need to set? That is probably pretty much it. So in other words, we will adjust the frequency by adjusting the prescaler in this case. And by the way, since the timer clock is 100 and we have to count up to 100 for, that was annoying, you have to press enter when you edit these values, otherwise it'll forget it. Now, so it'll count up to 100. So in other words, without a prescaler, it will run at 1 megahertz. And if I set the prescaler higher, then it'll run with a lower frequency. And that is pretty much all there is to that. So, as usual, let's generate the code with this. And there we have it. The code has been generated. It will have a timer 4 set up here. Now, first thing we need to do is, of course, to start the timer. We can do this. I actually have this, I played around with this before, so I have some code I can just copy paste. Well, let's see what we do. We fire up the PVM on timer channel 4. So it starts generating some code. Now, I would like to be able to play around with different frequencies. So what I have done here is up in private variables, I have created some variables here. And let me see. So if I put that, oh, where are we here? There. So I have created an array I call PVM, pulse width modulation vals, and here we have a prescaler, so 20,000, will be around 50 hertz, right? And a duty cycle of 10, 50, 90, then it will go down to 10,000, which will be a frequency of 100 hertz, and then it'll go all the way down to 1, which will probably be a it's count 1. So that will be a max frequency here of 500 kilohertz. Now, 500 kilohertz, where are we? There. Is way more than this scope can handle. This scope claimed to be 100 kilohertz, which is, let's just say that's bullshit. It will start trailing off around 40 kilohertz or something like that. It can do audio frequencies quite well, but that is about it. And then we have an index down here. That indexes where we are in this array. So now that we have all these values, what we can do down in our main loop is we can, where are we? We're here. We can actually add a next change. We want to change immediately because we want to set these values right away. So we can do an extra block down here. If now is bigger than, we set the prescaler to whatever we are at. We do that by setting the prescaler of timer 4 and then we are setting the compare value of TIM channel 4 to the duty cycle that we have, and then we have the, if we are getting bigger than the maximum test, then we cycle around and do it all again. Now for this, actually let's do it every second for now, so we can actually go through them pretty quickly. So I think that's all. Let's try to run it, and let's look at the serial output. There we go. So it sets, it cycles through the values, as you can see. Wait, there's a problem here with my video. Let's see if I can get that fixed. Where are we? Device. It doesn't really show anything. This is a bit awkward. Did it fall off? Yes, it did. Oh, shit. There we go. Oh, it keeps falling off. Here we go. You can see the changes here, and let's wait until it gets down to a low frequency again. There we go. Actually, let me show, probably here, we can see the device up here, and we can see the output down here. Sorry about that, but the point being here that we can now cycle through these values. We, if we look at the output, we set the prescaler to a value, and we set the duty cycle to a value, and we cycle through them. So we have this output on TIM 4, channel 4, which goes out on the pin we call PB9. So that is basically the output. Now, if we want to measure that, and let me clean up the screen a bit there. I'm still there, but that's okay, I guess. We can measure that by enabling our timer, another timer, and I have already, I have hooked up a cable between this PB9 and then we, wait, timer, and what we will do is we'll use a feature here called combined, and we will measure. Before we were using this in encoder mode, but now we'll use a PWM input on channel 1, and that actually, wait, I think I'm using this one. That's the one I hooked up. So TIM 2 channel 1. We will use this one instead. Yes, and now these will just leave completely, but we need to give it a clock source. So we will, no, we don't, sorry, we're using input capture, so we don't need a clock source. Yeah, we do, internal clock. We need the clock source for the counter to start counting time. But we will run it at full speed, no division, and input trigger, everything should be okay for this. We will need to enable the interrupt, so we are enabling the type 2 global interrupt. So this will actually interrupt. What happens when you do this is that you're actually running two timers, two channels, not two timers, but you're running two channels. So you can see when we set this combined channel, both channel 0 and channel 2, you can't use them for anything else because both channels are being used to measure these frequencies. So I think that's it. I enabled the, let's generate the code again. Now, first of all, we need to start these timers. So let's wait. Again, I'm going to use the code I already have. So up here, after we started the pulse width modulation, we can fire up this. So you can see you start the timer in interrupt mode on channel 1 and just start the timer on channel 2. So the rising edge, it will give an interrupt and we can do the measure. We can look at the timer values to measure. The second channel, falling edge, just stop the second counter. It will just stop the counter, but the timer channel 1 will still be running. So we get two measurements. We get the complete duty cycle and we get the active one, so to speak. So let's create the interrupt up here, and as usual we'll do that with a timer. So held time input capture callback, and if it is the correct counter, then we will store two values, counter full and counter. We need those values. We need those variables here. What we will do is we'll do them up here under the private variables. We will have the count full and the count high, and we will have a couple of floating points we will later use to calculate the floating point values of this. But we won't do that in the callback. We'll just store the data. The last thing we need to do is to do a little stuff down in our main loop. I think in an early version of this, I actually calculated those floating point values up in the callback, but there's really no reason to that. It makes more sense to do it down in our next check. So when we get the next check, we can calculate this. Did I set, I didn't say that, set this one. We need to set that up in the private defines. So define timer clock frequency 100 megahertz, right? So let's see the calculation again. We will take that 100 megahertz and we will divide that by how many counts we got for the full one. That will give us a frequency. And then we can count the high ones divided by the full one and multiply by 100. That will give us the duty cycle. So I'm trying to do two things at the same time. That's never a good thing. So let me actually print out that stuff. So yeah, we will have the tick, we will have the count, we will have the frequency that we print out as a floating point. Let me try to build it. It will probably warn or fail. There's a problem. I think I might have made a mistake. No, they're fine. I know one problem, and that is I need to go into the project properties, settings, and up here we need to click this to be able to print floating point values. Project, build project. Oh, not sure what happened there. That is much better, and no warnings. Let's try to run it and see what happens. Well, I want to make one more change in here. Next, I want to run longer, so let's set this one to 10 seconds. So now let's try to run this and look at the output. It fails. That's in. Okay, I know what happened there. We don't give a new line. So it was actually running. Now, let me show you this. I have argued many times that yep. Okay, I have argued many times that it may seem silly, but I will usually blink the LED. You can see it over there. I'll usually blink the LED in the main loop, and when I'm developing stuff, and it gives me a really quick way just to look, did it crash or did I do something else wrong? If it had crashed now, if it went into the error handler, then we would have had if it had gone into the error handler, it would have stopped blinking because we disabled the timer interrupt and everything. So it's a good way to see if the stuff is still running. So let me try to flash this again to start in the loop. So let's talk through what actually happens down here. So we are setting to almost 20,000 and compared to 10. So 50 Hertz, 10 Hertz. Now, wait. There's something really weird going on here. My toy scope is acting silly. Probably I need to find a better way to hook this up. I set the trigger wrong. You can probably not read that, but I can read that it says 10 kilohertz, the measuring, and does that match? It matches with, let's set, let's set this one, so you can actually see what is happening. So you have the frequency that it measures there, and you have the picture of the scope. Now let's try to start this again. Let's fire that up again. So it starts with 50 Hertz. Now, there, and it says 50 Hertz on the scope. And it should be 50 Hertz with a 50% duty cycle. and now it switches to 50 Hertz with a 90% duty cycle, and then it should switch to 100 megahertz. There, 100 megahertz, and the scope says 100.00 hertz. So in other words, we are using the timer in input capture mode to measure the frequency and duty cycle and calculate, and it is precise. I would actually say that this most likely can run better than my scope. It is more precise because see what happens on my scope when I get up. We are now at 1 kilohertz, 1000 hertz. That's fine. Still, I can deal with that. The scope can deal with that. Let's see what happens when it goes up to next. Still 1000. Now it should switch to what? 10,000, so 10 kilohertz. Scope is still okay with that. It measures the full, the top of the voltage is about, 1 volt per division, so yeah, it's not very precise. I didn't say, let's do that then. Let's move that down to roughly there. So you can see it is about 3.3 volt. But you can see now it is 20 kilohertz and it's already struggling to actually, well, at least for this one, it has a slow rise time. That could also be the jumper leads and all kinds of shit. It's not really well made, but you can see already there I'm starting to have problems. You can also see vaguely that there is an overshot. Okay. Now it is 40. It should still be okay. It is still 3.3 volt roughly that it is measuring, so it's not too far off, but you will see that when we drop this further, it will start. Now it's 40. Next one, I think it will start dropping significantly, and the time base, that is as good as I can do on this scope. So there, now we're at 100, and you can see it can barely do that, and it doesn't. Well, it can actually, kind of. Yeah, but it's definitely not a 100 kilohertz scope. But they are cheap, and for just toying around for videos like this, it takes a lot less space on my desk, and I'm actually quite happy with those. They're called Wave 2 Chinese scope, and you can build them as a do-it-yourself kit where you can put it together yourself, or you can pay a little bit extra and they'll do it for you. It's actually, but you can see 200 kilohertz. It's not ideal. Where are we? Let's get this up again. So I don't think I'm going to, I hope I explained this well enough. So we're using two timers, right? We are using timer 4, channel 4, to generate PWM, which we then cycle around. The timer 4, we are changing the frequencies by changing the prescaler only, and we're using the counter period so we can change the duty cycle. And then we are using timer 2 in input capture channel 1 down here. So you'll use channel 1 and channel 2 counters to actually count these things, and they will count the number of, well, I mean, that's why we needed the internal clock. It will count the number of internal clocks while it is running, and then it'll reset on the falling edge. So when it falls, it will reset the counter and it will give you the interrupt. And in our code, when that interrupt happens, we will read those captured values from channel 1 and channel 2, and they will give us the count full and the count high. And based on those two values and knowing the timer clock, which we do, we can calculate down here quite simple. We can calculate, oops, it is here, a floating point value of the frequency and a floating point value of the duty cycle. That's pretty much all I wanted to say in this video. I want to show you one other thing. I have created a Patreon page. Now, if you want to support this channel, and it would really be appreciated because quite a lot of time is going into making these videos, you can basically become a member over at Patreon and give us a tiny little amount of money, and that will help us go on. What I am going to do is I am going to post videos on Patreon first, and then a couple of days later I will post them on YouTube. But you can also get them on Patreon without advertising, so that's another benefit. You can see the last, at the time of recording this, where is that? That is here. You can see that 57 is the last video that has been published. But if we go over here, 58 has already been published on the Patreon page, and 59 has also been published on the Patreon page. So these will be the next two YouTube videos that are coming up. And when I'm done recording this, this will go on the Patreon page straight away. So, I mean, if you want to, please head over and check our Patreon. It is very much appreciated. I think that's about it. So, as usual, have a wonderful rest of the day.